Okay, so what we're going to do right now is just a quick little intro to electro and thermo, just in case you see some of these problems if you're taking practice tests. So in electro, basically what we're doing is we're kind of just reviewing redox in the beginning, because it's important that you understand that in a battery you have two parts to a cell. There's the oxidation part and there's the reduction part, and you're not going to have one without the other. And so if you were to look at a battery, a voltaic cell, then you'll see that the electrons will start to flow from one direction to another. And a really easy thing to remember is that the electrons will always flow. If you have a red cat, meaning the red wire goes where the cathode is, and the black wire we're going to call anox. And so it's really easy to remember because red cat, that's your cathode, versus anox, where oxidation happens at the anode, the electrons will always flow away from the ox and toward the red cat. So if you thought about this, and you saw a red cat over on one side, and you saw an ox over on the other side, you naturally don't want to start running toward the ox. Instead, where do you want to go? Toward the red cat. So the electrons are always going to flow from an ox toward the red cat, and that's just kind of a one thing to make sure that you keep in mind. And so that's the beginning of the notes, is just reviewing redox, oxidation, reduction. Remember Dr. Yuo? If you take a look, and the easiest thing on a redox problem is you write your oxidation numbers, which you just get your oxidation numbers from figuring out positive, negative, overall charge. So if this is equal to -1, you figure out that nitrogen's a -3, then the carbon must be a +2. If oxygen's a -2 and overall's a -1, then your Mn must be a +7. So once you figure out all your charges, you basically check to see which one's changing. Well, here I've got carbon at a +2, and over on the other side, I've got carbon at a +4. Well, I can see right there really quickly, if this were a multiple choice question, I can see that my charge is going up. And so the name is Dr. who? Dr. Yuo. And so this is the one that's being oxidized. Whereas the Mn right here is going from a 7. If I do this down to a 4, this charge is going down. And what does down go with? That's Dr. reduced, so down reduced. Now, you can also say Leo says Ger, and what Leo says Ger is going to help you with is, what does it mean to be oxidized? Anybody remember what the L and the E stand for in Leo? Lose electrons, oxidized, so then what's Ger? Gain electrons, reduced. Perfect. And you're going to need to know both of those, because maybe they say to you, which one of them loses electrons? And so then you could say, well, Leo, lose electrons, that means it's this one right here, versus the one that gains electrons. If you're ever asked for the agent is the opposite. So the one that's reduced is your oxidizing agent, and the one that's oxidized is your reducing agent. So the agent is simply the opposite. If you're ever asked how many electrons are transferred, when you figure out your least common multiple between the two, so for this one it's 7 to 4, so that's 3 electrons, and this is 2 to 4, so it's 2 electrons, and you always write the electrons on the higher side so that they balance out and equal. Then you want to figure out the least common multiple between a 3 and a 2, which in this case would be multiply them to get 6. And so then we would multiply this one by 2 and this one by 3, and these are what you're going to use to put your information back into the balanced equation. And so we would say that 6 electrons are transferred, so it's once you figure out that value, then that's how many electrons are transferred. So that's just a quick review of redox. So in addition, what we start talking about is electrochemical cells. And in these cells, in these batteries, you have one ox and one reduction site. So you're not going to have 2 ox or 2 reductions. And typically what will happen is you'll be given a chart that just shows reductions, okay? So if you think reductions, you're thinking the charge is going, what's the guy's name again? What's his name? Dr. Yuo. So you're thinking down, reduce. You're looking for the charge going down. And if the charge is going down, then what happens is your electrons will be on the left side, okay? Now, you're going to be given reduction potentials, and you need to figure out which one is the oxidation one, okay? And so what you basically do is you check to see what your values are of your cell's potential, and depending on which one is more negative, that's the one that you are going to flip and make your oxidation site. So if they give you a bunch of reductions, then you always want to flip the one that has a lower value. That way, when you add the two together, you get a positive E cell, and I'll talk about that later on as well. So there it is, the anox and the red cat, and this is just showing a battery. And we'll go through all of these notes later on, and same thing here. Okay, so in this one, this is what I was talking about. This is a battery, and it would be a nickel and potassium battery that was made here. And so there's a chart that you'll be given that has all of the reduction potentials on it. Again, they only show you reductions. They don't show you oxidations. So this I can see is going from a plus charge to a 0, and this is going from a 2 plus to a 0. Remember, if it's just in the solid state, it's just 0 charge. So both of these are going up or going down in charge. They're both going down, which again means that these are being reduced, okay? So these are reduction potentials. And on the chart, it'll give you your E cell value. And it says negative 2.92 and negative 0.25. Which one is more negative, is a bigger negative number? The first one. That's the one that you would actually reverse and flip. And when you do that, you'll get a more positive E cell value when you add the numbers together. So then you add the two numbers together, and then that basically gives you what your E cell value is. That's pretty much it. I think that's probably a big thing. And we'll talk about spontaneity. I'm going to show you thermo real quick. Okay, so let's go to thermo. So 3 major things: delta H, delta S, and delta G. Delta H you know already, because we did that back when we did Thermochem. And delta H is just called enthalpy, right? And in order to figure that out, you do products minus reactants. Remember, you do this. If there's a coefficient, you have to multiply by 2 or multiply by 3 or whatever it is. Okay, and then you just do your products minus your reactants, and you get your answer. Entropy works exactly the same way. You can be given a chart, and so in that chart, you may be told what the values are, like here, of entropy. The only difference is these are measured in joules. Delta H is measured in kilojoules, typically. So what that means is, if you're going to use the two together, you have to convert this into kilojoules first, okay? That's just one thing to remember. So let's talk about what this entropy is. Delta S entropy tells you how disordered a reaction or a solution is. So if you start off as something being all solid and it turns into all gas, are you becoming more disordered? Is it becoming more disordered, yes or no? Yeah. Yes. So gases are moving around and flowing around, whereas solids are all compact all together. That's increasing in disorder. We would say that the delta S is positive in that case, okay? If the reverse happens, and let's say that you have a whole bunch of gaseous molecules, 2 something plus 3 something that are gas, and then you get 1 solid or 2 solids, something like that. So your gas is turning into a solid. What's happening to your disorder? It's actually decreasing in disorder, and your sign would be not positive, but negative. Okay? So that's it for entropy. And the last one is delta G, and this is called free energy. And basically, how much energy is available after your reaction takes place, it tells you whether a reaction is spontaneous or not. So I just wanted to introduce this word to you. Spontaneity is basically, will your reaction proceed without the addition of outside energy? That's what spontaneity is, okay? So will it go from this to this, and you did not have to supply any energy? It tells you nothing about kinetics or time. It just tells you, yes, my reaction will proceed in that direction without supplying any energy, okay? So this equation, I call it the hats equation. So I say that Gibbs wears hats because there's a coach named Coach Gibbs. I think I might have a picture of him. And there he is. There's Coach Gibbs. So the Redskins, how many of you know this coach? Some of you may know. Okay. And so he always wears hats. And so I was like, I happened to look at pictures, and I was like trying to look up some analogy to get you guys to remember. And I found out that he always wears hats. So Coach Gibbs always wears hats. And so I call this the hats equation. And it's delta G is equal to delta H minus T delta S. And so the idea is that if you can figure out any 2 of these, you can figure out whether or not your reaction is spontaneous. And so what I say is, I say that Sarah eats gross ham. Everybody say, Sarah eats gross ham. Sarah eats gross ham. Sarah eats is a positive thing, okay? And so if you have a delta S, your delta S being positive, that's going to favor a spontaneous reaction. And a positive E cell is also going to favor a spontaneous reaction. The G needs to be negative. Delta G needs to be negative. This actually tells you whether or not you have a spontaneous reaction. And delta H, we also want delta H to be negative, because if that's negative, that means it's an exothermic reaction. So these two, though, you cannot figure out whether it's spontaneous unless you know both of them, okay? So you need to be told about both. You cannot say an exothermic reaction is spontaneous or a reaction that's increasing in disorder is spontaneous. You need to check both of them out, and you need to see if one of them basically trumps the other one, you may or may not have a spontaneous reaction. So what you want is, you want delta G to be negative, you want delta H to be negative, and you want delta S to be positive, okay? And this would basically be in favor of having a spontaneous reaction, okay? And that's basically all I wanted to show you. I think even on this page, we just started talking about what happens if you have a negative H and a positive S. It's always spontaneous. But what if the reverse happens? Well, that means that it's decreased. That means that it's endothermic and it's decreasing in disorder. That's never spontaneous. So you may see questions that are like that, and I just kind of wanted to highlight a little bit of that. Okay. Last thing that I wanted to look at is titrations. Okay. And so just to make sure that you have a good idea about what happens in titrations. So if you have a strong acid being titrated with a strong base, and in this case, I'm starting at a pH of about 1, which means that inside of my flask, I probably have what? An acid. And over time, what's going to happen is, you're going to start to slowly increase, but this is called, there's a certain amount of buffering that happens that maintains the a pH, and then all of a sudden, there's this huge shoot up right at this point right here, and they call that the equivalence point, okay? And so this like point of inflection basically is where that equivalence point is. What does the equivalence point represent? Where what is equal to what?
Base is equal to acid.
Acid is equal to base, but what of the acid and what of the base are equals? Not concentration, but not concentration. MAVA equals Mervet tells you that what is equal. What do you get when you multiply M times V? Moles. Awesome. That's where your moles of acid are equal to your moles of base. Not concentration, because you could have different concentrations. And so this is at pH 7, if you have a strong acid, strong base, your equivalence point is going to hit at pH 7. So then I wanted you to take a look, and this is showing it again where you're at pH 7. Okay, and so now let's take a look. On this one, we're starting with an acid, but look at this line I guess when we compare it to this one here. This was our strong acid that we were looking at before. What do you think this one is? A weak acid, because the pH is at 3. And now you can see, where does your equivalence point happen? It happens at more of a pH like what? 9. So when you titrate a weak acid with a base, then your pH is actually, with a stronger base, your pH is going to be more basic at the equivalence point. Okay, and let me show you one more, or two more. On here, so this is a strong base with a strong acid, so we're starting at a high pH, and then same thing, your inflection point is right about here, which hits at a pH of about what? 7. But this is a weaker base, and if you do a weak base with a strong acid, where does your inflection point hit there? More like what? 5.5, something like that. And so you can see that your pH at the equivalence point is actually more acidic. So if you have a strong acid, then at the equivalence point, your pH will be more acidic. Okay, and this is the last thing is, what happens if you have a diprotic acid or a diprotic or triprotic acid? What I mean by that is H2 something or H3 something. What do you notice that's different about this graph than about the other ones? There are 2 of them. And now let's take a look at what happens if you have a triprotic acid, and what do you notice here? Yeah, so you've got multiple points of inflection, and this one, you don't even see. The third equivalence point is up here, which is kind of weird. It looks like more of a slant, because it's not even a strong amount of hydrogen ions that are being released. So it's not a strong acid that's being released. All right, and that's basically it for just kind of covering a couple of those topics.